Two containers sit on the same machine. Each one is healthy. Each one is running a web server. And yet, when one tries to reach the other, the request vanishes into silence. That is the quiet crisis Docker was built to solve. Containers are deliberately isolated, separate rooms with their own network interfaces, their own addresses, their own routing tables. Isolation keeps one broken service from tearing down everything around it. But isolation also means cooperation is not free. If addresses change every time a container restarts, how does one service ever find its partner? Tonight we follow that problem from the locked room to the open door. How Docker networks let containers talk, how ports punch a controlled hole to the outside world, and how a simple private network turns strangers into collaborators by name. Under the hood, Docker does not magic connectivity into existence. It borrows three ideas from the Linux kernel and wires them carefully. First, network namespaces. Think of each container as getting its own private networking universe, its own interfaces, IP addresses, and routes. What happens in one namespace does not leak into another unless you deliberately connect them. Second, virtual Ethernet pairs, often called VETH pairs. Picture a virtual cable with two ends. One end lives inside the container. The other plugs into a bridge on the host. That is the physical metaphor for how packets leave a container at all. Third, IP tables rules on the host. These are the traffic cops, network address translation, port mapping, who is allowed to reach whom. Together, namespaces, VETH pairs, and IP tables are why a container can feel sealed shut and still, when you choose, speak to the host, to other containers, or to the wider internet. The tension never goes away. Every network choice is a trade between isolation and reach. Docker packages those trade-offs into network drivers, different personalities for different jobs. Bridge is the default. It creates a private network on a single host. Containers on that bridge can talk among themselves. To reach the outside world, you still need port mapping. It is the careful middle path. Host is the speed demon. The container shares the host's network stack outright. Performance improves. Isolation vanishes. If something binds port 80 on the host, your container is right there in the same neighborhood. None is the hermit. No network access at all. Useful when a workload should compute in total silence. Overlay is the multi-host diplomat. When containers must span several machines in a cluster, overlay carries their traffic across the fabric. MAC-VLAN dresses a container like a physical device on your local network, complete with its own MAC address, handy when legacy systems expect real hardware. And then there is the user-defined bridge. Still a bridge, but one you name and control, with a gift the default network does not emphasize as cleanly. Containers can discover each other by name, not only by shifting IP addresses. Choose the driver, and you choose how much isolation you are willing to spend. Here is a moment every beginner hits. You pull the official Nginx image from Docker Hub. You run it. Docker reports a container ID. Inside that tiny world, Nginx is listening happily on TCP port 80. You open a browser on the host and nothing. The server is running. The page never arrives. Why? Because a container's ports are private by default. Exposed ports in an image are documentation and metadata. A note that says, this service intends to listen here. They are not the same as published ports. Publishing is the deliberate act of mapping a port on the host to a port inside the container, so outside traffic has a doorway. Until you publish, the locked room stays locked, even when the lights are on inside. The doorway is one flag, -P. The full pattern is host IP, then host port, then container port, optionally with a protocol. TCP is the default. UDP is available when you need it. In practice, the command you will type looks like this. Docker run -P8080:80, name the container web host, run it detached with -D, and use the Nginx image. Read that mapping left to right. 8080 is the port on your machine. the one your browser will hit at localhost. 80 is the port Nginx already uses inside the container. Detached means it runs in the background, so your terminal stays free. You can confirm the intention with Docker inspect. Filter the output for exposed ports, and you will see 80/TCP listed for Nginx. That is the internal story. The -p flag is the external story. After you publish, the welcome page finally loads, proof that the bridge from host to container is open. The same logic is not limited to images you download. Build your own. A typical React example starts from a Node Alpine base image, sets a working directory, installs dependencies, copies the app, and declares expose 3000. That expose line does not open the port to the world. It documents the contract. This process listens on 3000 inside the container. You build the image with Docker build, tag it something like basic React app, then run it with -p 3000:3000. Host 3000 maps to container 3000. Open the browser and the app appears, not because Docker guessed, but because you published the path. Notice the pattern. Whether Nginx on 80 or React on 3000, the mental model never changes. Inside port, outside port, and a conscious mapping between them. When the browser stays blank, you need a short diagnostic loop, not guesswork. Start with Docker PS. It lists running containers and shows which host ports map to which container ports. Next, Docker port followed by a container ID prints the bindings in plain language. Formatted Docker inspect can filter just the network settings or exposed ports, so you are not drowning in JSON. Docker image inspect does the same for the image metadata before you even run anything. There is also -P. Instead of choosing the host port yourself, Docker publishes every exposed port to a random high-numbered port on the host. Convenient for quick tests, awkward when you need a stable bookmark. Remember the quiz that trips people up. Docker run nginx alone fails from the outside not because nginx is broken, but because no port was published. The service is alive in its room. You simply never unlocked the door. Ports solve the outside world. What about containers that must find each other on the inside? List what Docker already knows with Docker Network LS. You will see the defaults, including the standard bridge. For a real application, create a user-defined bridge of your own. Docker Network create my-app-network. Optionally, pin the driver explicitly with create-driver bridge and a name like demo-network. At birth, that network is empty. No members, no gossip, just a private meeting room waiting for guests. The point of naming it yourself is isolation from unrelated containers, plus automatic service discovery. Once two containers join, they can address each other by container name instead of chasing IP addresses that change on every restart. Who builds the meeting place? You do, with one create command. Now invite the guests. Run 2 Nginx containers and attach them at birth. Docker run -d, name web-server-1, network my-app-network, image Nginx. Then the same for web-server-2. Both land on the same user-defined bridge. The empty room suddenly has residence. You can also connect a container that is already running. Docker Network Connect, the network name, then the container name or ID. Membership is not a one-time wedding vow. It is a living attachment. Inspect the network and the JSON grows a containers section. Names, endpoints, IP addresses. That is the roster. Two services that once could not see each other now share a private LAN on the host, ready to cooperate. Here is the payoff that makes user-defined bridges feel like magic, and it is really just good bookkeeping. From inside Web Server 1, run docker exec-it web server 1, then curl http://web-server-2. No hard-coded IP, just the name. Docker's embedded DNS on that network resolves web-server 2 to whatever address it currently holds, and Nginx answers with its welcome HTML. That is service discovery in miniature. Front ends find back ends. Workers find queues. When a container restarts and receives a new address, the name still works. The brittle spreadsheet of IPs can finally be thrown away. After the request succeeds, the story on screen is simple. One container spoke a human name, and the other container answered. Architectures change. Membership should too. Docker Network Disconnect My App Network Web Server 1 removes that container from the bridge while it may still be running. It leaves the party without being destroyed. Connect and disconnect are the sliding doors of application topology. When a network itself must go, first ensure nothing still references it. Docker will refuse to remove a network that containers still cling to, a small, stubborn safety rail. Then Docker Network RM deletes a named network. Docker Network Prune sweeps away every unused network in one pass, the janitor for experiments you forgot to clean up. The operational loop is symmetric. Create, connect, inspect, list, disconnect, remove, or prune. You are not stuck with the first drawing of your system. You redraw the lines while the city is still awake. So we return to the opening silence. Two healthy containers, unable to cooperate, were never a failure of compute. They were a failure of introduction. Docker networking supplies the introductions. Namespaces keep the rooms separate. Veth pairs and bridges lay the hallways. IP tables and published ports cut controlled doors to the outside. Drivers let you spend isolation for speed, or for multi-host reach, or for absolute quiet. A user-defined bridge gives services names they can trust. Connect and disconnect let the map evolve. What this knowledge makes possible is ordinary and profound, microservices that find each other, development stacks that mirror production edges, and demos that finally load in a browser on localhost. The question the field keeps chasing is not whether containers can talk. It is how much isolation, speed, and reach each new system should trade, and who gets to open the next door.